This method can be long. Euler's method can take a lot of time, especially if you have a really small value for h. So I'm going to show you how to automate this process in Excel. So my first column is my n values. I start with n equal to 0, and we went up to n equal to 4. We have our initial point, x0 is 0, y0 was 1, and our differential equation just said that the derivative dy dx is equal to y. So we need that f of xn, yn is equal to yn. And once again, we're going to use h equal to 0.25. So we know for this we need to take our previous value for x plus h. And that gives us our next value for x. We can put dollar signs around the f so that that cell does not change when we copy down the formula. And we get all of our values for xn. For yn, we knew it was equal to the previous value plus h times f of xn, yn. And once again, we're going to put the dollar signs around the h value since that's going to be constant in all of our formulas. We also know that the differential equation just said dy dx is equal to y, so the next value for y is just going to be that same value. And we can keep going on this process and copy it down. We get 2.441, just like we did before. And this can be very nice because if I change my value of h to something like 0.125, so even smaller, I can extend this down. This time I'll need to go down to 8 values. And I can copy these formulas down, and this time my approximation is 2.566, which is actually closer to the real value. If I change h to 0.0625, this time I'll need up to 16. And once again, I can copy these formulas down. And this time my approximation is 2.638. And the idea being the smaller and smaller h gets, the better and better of an approximation we have. If we were to do this by hand, it would be very, very long and drawn out. But we can make h super, super small this way with this kind of automation, which will then give us better and better approximations without having to do more and more work. We can split h in half again. This time we'll need 32. And then we can once again copy our formulas down. And this time we have an approximation of 2.677. And like we said before, the actual value is 2.718. So the more and more values we do in this process, the closer and closer we'll actually be. So the smaller and smaller value of h, the better and better of an approximation that we have.